number 1, we're integrating cosine to the third x, sine to the fourth x, dx. And where this falls into, whichever lesson it was where we integrated odd powers of cosine x and sine x. And when we were integrating odd powers, remember, we'd take that odd power and we would break it up into pieces. And so in this case, our odd power is cosine cubed x. So that's the one that I'm going to break up into a cosine and a cosine squared. And I think I switched the order here. So I'm going to write an extra step that I didn't write on the review worksheet. But I'm going to put sine to the fourth x first. And then I'm going to take cosine to the third x, and I'm going to break it into cosine x and cosine squared x. And then, of course, that is all dx. Okay, so I still have all the same pieces there, right? I still have sine to the fourth. Cosine cubed, I broke into cosine and cosine squared. Now, we have an identity for cosine squared that we're going to replace it with. In the meantime, sine to the fourth x and cosine x are going to stay the same. What do we know about cosine squared x? Yeah, 1 minus sine squared. That is the Pythagorean identity that sine squared plus cosine squared is 1. So cosine squared is 1 minus sine squared x times dx. Now I want to think about a distributive property where you are taking this sine to the fourth x cosine x and we are distributing. Okay? So as we do this, sine to the fourth cosine x times 1 is just going to be sine to the fourth x cosine x. And I'm going to go ahead and say times dx, because I think you guys will be okay if I go ahead and break it into two, sorry to say radicals, wrong class, integrals. And then minus, and now multiplying sine to the fourth cosine x by sine squared. So that's going to become sine to the sixth x cosine x dx, not du. Okay, as we go to integrate this, at the time I taught it as a u substitution. I don't know if you still need to think that or if you are pros enough now you don't, but in terms of u substitution, the one with the power is what I make u. And so I would think of this, my u substitution, u is going to be sine x. And if u is sine x, then the derivative of u is du, derivative of sine x is cosine x dx. And so then if it helps, you can think about this as, okay, I'm integrating sine to the fourth x. Well, that's really thinking sine is u. So that's u to the fourth. Cosine x dx is replaced with du. Minus. I just heard Minnick's voice out there. The integral. Sine to the sixth. Well, that's going to be replaced with u to the sixth. Cosine x dx is your du. And then we're integrating those. Okay? Integral of u to the fourth. 1/5 u to the fifth. Minus integral of u to the sixth. 1/7 u to the seventh. And then, of course, with integrals, we're always going to say plus c. Of course, we're not just going to leave it in terms of u, though. We're going to go back to, what was u? Sine. So 1/5 sine to the fifth x minus 1/7 sine to the seventh x plus c. Does that ring the bells? that one you were absent for, Maddie, when I taught it? Or were you here?
I don't know.
Okay.
I don't know. What was confusing me is I got it wrong. But I was like, oh, and then I went to look back on the answer page, and you have this sign in front, and it threw me off, and it just, but I get it.
Okay. Yes, Abby.
Do you mind if I go over number 2?
Not at all. Number 2 is actually a good one. Number 2 is a type that I kind of warned you of previously. I am going to go another screen, though. I could fit it over here, but... There we go. Number 2. The radical, or integral, my goodness, of x minus 2, or square root of x, dx. Okay. As number 2 looks now, it's kind of ugly. Okay. However, I guess it's kind of ugly, and I don't really have a way to work with that. However, that denominator is one term. Okay. That denominator, the square root of x, is the same thing as saying x to the 1/2. And the idea here is that I can divide both pieces by x to the 1/2 and make it 2 separate terms. So I'm kind of taking extra steps here, but the idea is I'm going to say, okay, x divided by x to the 1/2 and minus 2 divided by x to the 1/2. I'm taking the super duper long way, but that way you can kind of see how I, magically jump it probably appears. Because now if I clean this up, okay, well, what is x to the first divided by x to the 1/2? Well, if the base is the same, subtract the exponents. 1 minus 1/2 is x to the 1/2. I can integrate x to the 1/2, can't I? Minus, here I have a 2 on top, x to the 1/2 on bottom. So the 2 on top is just a constant 2. What do we know about x to the 1/2? Take it out of the denominator, and it's x to the negative 1/2. So I can think of this as 2x to the negative 1/2. And that I feel more confident in integrating. Granted, it's fractions. I didn't say it was the easiest integrating, but it's still much more doable than some others. So the integral of x to the 1/2. Add 1 to 1/2, and that gives me 3/2. Divide by 3/2, which is multiplying by 2/3. Minus, okay, I already have a 2 out front. X to the negative 1/2. Negative 1/2, add 1 puts me at positive 1/2. Dividing by 1/2 is going to have me multiplying by 2 to the 2 that's already out there. And then, of course, it's an integral, so I'm going to say plus c. If I clean this up, 2/3 x to the 3/2 minus 4 x to the 1/2 plus c. I assume I didn't go back to radicals there. No. Some of those extra steps help along the way there. Okay, next. Several good ones I see. I don't know where.
13.
Oh, we can go for 6.
I can't find A and B either, so.
13's always good, right?
I say piecewise, so.
Okay, see, she sees A's and B's. You see piecewise.
Struggle is real. But
Okay, find values for a and b that make f of x continuous. What makes something continuous? We actually talked about this yesterday.
Limits.
Right. And I didn't really put that on here, but that's essentially what my brain did. Okay, so the idea is the limit as x approaches 1 from the left of f of x needs to equal the limit as x approaches 1 from the right. Okay? And technically it also has to equal that point, which in this case that point is included right here, so we should be okay. What is the left side?
The absolute value there.
Okay. So when we say the limit as x approaches 1 from the left, well, that's when x is less than 1, so absolute value of x plus 3. That's going to have to equal the limit as x approaches 1 from the right. As x approaches 1 from the right, that is the ax squared plus bx. That's where x is bigger than 1. Yeah, I don't really know why I wrote what I wrote. I feel like I didn't really give the whole thing here. How do we do a limit?
Plug in.
You plug in the value, right? Unless you run into issues, you plug in the value. So when you plug in the value, the absolute value of 1 plus 3 is going to be 4. And that has to equal this other limit. When we plug in 1 over here, it's a times 1 squared plus b times 1. 1 squared is 1 times a plus b times 1. This just becomes a plus b. It's just asking continuous. That's all the information we have, folks. So find values of a and b that make it continuous. Any values where a plus b add to equal 4. Okay? Okay? Next.
I just have a quick question about 11. The limit from the left is equal to the limit from the right, but it's not necessarily continuous at that point.
Okay, so on 11, is the following true or false? If f is a function such that the limit from the right equals the limit from the left, then f must be continuous at x equals 2. This does not address what the value is at 2. And so that's why we can't say that it is definitely true. Like the problem I just did, the difference with the problem I just did is that I can see, okay, this is x greater than or equal to 1 here. And I know when I put in 1, that's making that value equal as well. I don't have any information about this function here. I just know it as f of x. And so the theorem behind it all says limit from the left has to equal the limit from the right, has to equal at that point. So it has to equal f of 2. But I know nothing about this function. Does that make sense there?
So it's because we don't know that it can equal to.
Right. In other words, this could be continuous, but they use the words must be continuous. And just because the limits are the same does not make it continuous. Because, and as, yeah, in the explanation I said, okay, it could be a whole. We don't know what f of 2 is. If the limit from x from the left and the limit from the right equals f of 2, then yes, it is continuous. But f of 2 could be a point somewhere else, and so that's why we can't say that it has to be continuous. So 11 is kind of a good follow-up on 13, really. It's going along the same idea, isn't it? So, yep. Same idea. Okay. Next.
Can we do 6?
said 6, right? Okay. Let me write the equation down. That's going to take me a moment. Y equals 5 to the x squared minus 1 minus the log base 2 of x cubed plus 1 plus the natural log of 3x plus 1. Now, it says to find the slope at x equals 3. The slope means I'm finding the derivative. At x equals 3 means I am putting the 3 in. So we're finding the derivative and evaluating it when x equals 3. So, Ross said there's going to be a lot, you just have to know the derivative rules, right? It's keeping all the rules straight. And that is a lot of what it is. So, y prime, derivative of 5 to some power is
5 to that power would be 5 dx.
5 to that power, how about times, isn't it times? Yeah, times the natural log of 5. Okay, so derivative of 5 to some power is 5 to the power times the natural log of the base, so the natural log of 5, times, if your exponent, if there's a chain rule, can we do the derivative of the exponent? So what's the derivative of x squared minus 1? And that's the 2x. So the basic derivative is 5 to the power times the natural log of 5. Then it's times the derivative of anything in the power. Minus. Now we've got to do our log rule. So the derivative of log of something. Derivative of log base 2 of something is 1 over. Remember this one? I struggle to remember this one, I'll be honest.
X, ln.
Yeah, it's 1 over x ln a.
Okay, so 1 over x ln a. So ln a is going to be natural log of 2. The x is x cubed plus 1. I have that order reversed on here. Okay, so 1 over x ln a is a good way to remember it. Where x is whatever the main inside is. Natural log of a is natural log of the base. Now times, can we do the derivative of the inside? Derivative of x cubed plus 1 is 3x squared. Plus, oh, I like this last one, it's easier. Derivative of natural log of something. 1 over the something times the derivative of something. What's the derivative of 3x plus 1? 3. Now, based on the fact I've put again 3, I would do some cleanup here. Let's see, did I clean up the first part at all? I didn't really. In hindsight, I feel like I'd write that in a different order. Because in hindsight, I don't know, I don't like that order, but I just kind of left it as this. 5x squared minus 1 times natural log of 5 times 2x. Minus, when I do this, I can make this a fraction and put 3x squared over x cubed plus 1 times natural log of 2 plus, and then over here I can say 3 over 3x plus 1. That's our derivative. We want the slope at 3. And we are plugging 3 into that business, yes? 5 to the 3 squared minus 1 times natural log of 5 times 2 times 3 minus 3 over 3 squared over 3 cubed plus 1 times the natural log of 2 plus 3 over 3 times 3 plus 1. You can definitely clean up some of that. If it says exact, you don't want to go like calculator version. You want to just go cleaned up version. Because that's approximate, it could be. 3 squared minus 1 is 8. So that is 5 to the 8th. 2 times 3 is 6. I'm going to go ahead and say 6 natural log of 5. Minus 3 squared times 3. I'm going to say 27 over 3 cubed plus 1. 27 plus 1, 28 over natural log of 2. Plus 3 over 9 plus 1, 10. The only way you can clean that up and give an exact answer would be to figure out what 5 to the 8th times 6 is. That's the only way. That's the only farther you can do cleanup wise, because 3/10 is 3/10. An exact answer, you would not plug in natural log into your calculator. Okay, an approximate answer you could. Honestly, this is probably a good way to leave it. My answer key says that 5 to the 8th times 6, which is what's happening there, is 2, 3, 4, 3, 7, 5, 0.
Wow.
Times natural log of 5, minus 27 over 28 natural log of 2, plus 3/10. Okay. A good way to check your work by hand, plug this answer into the calculator and get a decimal answer, and go back and use your inderiv and do the derivative, evaluate it at 3 and get an answer. That's a good way to check your handwork if you have the calculator available, but you need an exact answer or something. Obviously on AP, if you had something like this on AP, you wouldn't, you would just leave it exact if you don't have a calculator. Okay. Moving along.
Number 9 tangent.
Yes.
Can we go over that again?
Yes. The question was, is number 9 tangent, and can we go over it again? I want to know if other people have a better way to teach this one, because I feel like I don't do a good job of teaching sine inverse and tangent inverse. I don't know. I feel like maybe they're just hard to see, but
Yeah, I still don't see.
I mean, they're harder to see. Now, to recognize here, is I see like a constant. Did I write that down right? Yeah. So a constant plus an x squared type thing on the bottom, and then the x on top. What is this one doing? Confused here on my own, but okay. One thing I always suggest, and I don't know. I guess I just have to do this to keep myself straight. What do we know the derivative of tan inverse of x is? Okay. She said x squared plus a squared. My hand started to write a squared plus x squared. Same thing, right? I just, without thinking. Okay. So, as we try and tear this up, couple of pieces of information. First of all, as we think about this being a squared plus x squared, right? If I'm trying to visualize that, my a is going to be square root of 5. because a squared is in place of 5, so a is square root of 5. I hate to say this, my quote x value, have to be careful there, right? 9x to the 4th is the same as saying 3x squared, right? Did I write it differently on here? No, that's... And so at that point, I would kind of think, okay, my guess, if you will, is that, okay, I think this is tan inverse of, oh, you know what, I said x here, this should say x over a, shouldn't it? X over a, so if we're saying tan inverse of x over a, my guess is tan inverse of 3x squared over square root of 5. So pretty, huh? Yeah, sure. Now, this is my guess is what I'm doing here. But I've got to figure out all these other pieces, right? Because is this 4x right? Or is this 4x wrong? Not wrong, but, you know, are there pieces I need to include in it? So then we're going to take the derivative. So if we take the derivative of tan inverse of this function here, the derivative of tan inverse of x over a is a. So what is a? Square root of 5 over a squared. So square root of 5 squared plus, quote, x squared, which is 3x squared squared. But then we have to consider times the derivative of the inside. And when I say the derivative of the inside, I'm talking about the derivative of the x value, not the a value, the derivative of the x value. So what's the derivative of the x value? The derivative of 3x squared, yes. That's what I'm trying to do here. The derivative of 3x squared is 6x. Now, how close are we? How close are we not? This is where we have to look at the pieces. Okay. We have the x is good, right? X is good, yes? Here, though, we have extra, and I guess I could have even put it together as one fraction, if you will. If I put this together, there's a 6 square root of 5 times x on top, right? Over the 5 plus 9x to the 4th. So the pieces that are not good, that 6 square root of 5 is not in there, is it? And then if you go and look at the original, we've got another issue. What's the issue here? There's a 4. Now, this 4 is just a constant. So the 4 I can just take out front. And so it's going to be 4 times my guess. Does that piece make sense here? So if I put that 4 out front, that's going to be 4 times my guess. So right here we had my guess, right? So my guess was tan inverse of 3x squared over square root of 5. This 4 out front says, okay, the rest of it's good. We're going to have a 4 out front. Now, what are we not compensated for?
We need to have a little over 6 square root of 5.
Right. There's a 6 square root of 5 here that comes up when we do chain rule and all that business. Okay? That 6 square root of 5 was not in the original problem. So to compensate for a 6 square root of 5, you're going to do 1 over 6 square root of 5. And that's to compensate for this one right here. Okay? How did I put this in the answer? Did I put it back together, I'm guessing? Yeah. If I multiply that together out front, it's 4 over 6 square root of 5 times tan inverse of 3x squared over square root of 5. course, it is officially an integral, so I should say plus c. You'll notice my final answer in the answer key, I did reduce 4/6. 4/6 reduces to 2/3. So 2 over 3 square root of 5. Tan inverse of 3x squared over square root of 5 plus c. And no, I'm not rationalizing. There's enough ugliness in this one, right? So that's my final answer. Obviously, there's some other forms there that could have happened in.
AP doesn't care, so I don't care.
Well, but multiple choice, you need to be able to recognize what it should
And
be.
we've had a few of those on the test where like I'll have the answer, but then it was like, oh, like they divided like the 2 over the y and stuff like that. And I was like,
Yeah.
oh,
Yeah, they will try and do sneaky things.
There was also, I think, on the last test, there was one that either didn't have a plus C, but was the correct answer, or didn't have a pi, and was the correct answer.
yeah,
I feel like there was one like that.
there was.
It's common.
Yeah, it's just like a bunch of one that like you would have got the answer if you forgot to square it. Oh yeah, they try to get us for sure.
Now these aren't even, unless you're talking about the AP exam the exam practice are actual AP questions. The ones on the test that we do in here are not actual AP questions, but doesn't mean you're not going to see the same tricks. So, okay, I guess we're about out of time here, aren't we? Unless there's anything quick you guys want me to.
So, because number 10 is in feet, what is the number for acceleration in feet?
32. So you'll notice when you look at the answer key on 10 that my acceleration function starts off as a of t equals negative 32. But then I have a asterisked comment, if that's how I should say that remember to use negative 9.8 if meters. So if they're giving you meters, remember acceleration is 9.8. If they're giving us feet, 32.
Yeah, I started that problem and then went to check my work and I was like, oh.
I don't know the
Yeah.
We mentioned that once. I don't know.
Yeah.
It's just weird because in all of physics, it was always meters.
Oh, always.
Well, and notice, why did I put that comment on there? If I'm guessing, the test is probably in terms of meters instead of feet. But you need to beware, right?
My biggest flaw is that I'll just like read like the number and be like, okay, that's the velocity, that's the height, and not even.
I need to check. I have several issues with this worksheet. Is everything?
I have a lot of studying I need to do tonight.
Yeah, I have an anatomy test, an AP Chem test.
Number 12. It says find the area of the solid by revolving this region.
It means volume, right?
That should say volume. That didn't get changed. The equations got changed there, but that didn't get changed. So if it says revolve, realize we're talking volume.
Yeah, I was confused on that part, but I just didn't see.
Just
I
just assumed typo. If you're revolving, it's volume, which is pi times the radius squared. So pi times the function squared.
Thank you.
If it's area, remember you're just integrating. Maybe you're subtracting it up or minus lower, but you're just integrating.
Awesome.